Hello everybody, this video is about the explainable artificial intelligence, SHAP with regression in Jupyter notebook. Okay, we need to install SHAP, SHAP. For this you need to go to Anaconda prompt. Jupyter terminal command prompt. So you need to type Anaconda install Anaconda dash forge column SHAP columns twice SHAP or pip install SHAP. Sorry, SHAP instead of SHAPE. Okay. Once you do that, come to Jupyter. You need to install importing. You need to import packages, libraries, functions as well. So you need to import Pandas as PD. This is for tabular data. And for generic math, you needed to import NumPy as NP, and then from NumPy you need to import absolute. Good. Now for modeling purposes, since you are in regression, you need reach from scikit-learn dot linear model. Then you need metrics. To evaluate the model with metrics. So from scikit-learn dot metrics, we need to import R2 score, mean, absolute error, mean squared error, same matrix and function as well. We need scikit-learn dot model selection. We need to import a cross-val score. And the train test is split. Cross-val score is for the cross-validation, and the train test is split is going to help us to split our dataset into training and testing. So both of them are from scikit-learn.model underscore selection. Good. Now we need SHAP itself. To run SHAP, we need to import SHAP. Then we need to initialize the JS on SHAP. So SHAP.NET.js. Then sometimes you may have some error message warning, error message warning, so we need to ignore them. So we need to import warnings, and then have warnings be filtered. Filter warnings. Ignore. Good. And then we need to make our codes reproducible. And by setting C to input 7. Good. So after installing SHAP, you import everything we need to run our model. Then now we read the data set. Type in my data equal pd canvas.read underscore comma separated value. The data set is found in this directory. Set tech docs data / flood 2 dot comma separated value. Comma separated value CSV instead of CVS. Okay. Exploring the data set. Let's type my data dot head to have an idea about the name of the columns and the first 5 rows of the data set. So have time, have area, this is the flooded area, which is our dependent variable or target, and we have ET, which is stand for evapotranspiration, P for precipitation, AT for air temperature, and the SM for soil moisture. These four are the independent variables or features. So if you want a brief descriptive statistic, type metadata.describe. And on the shape or the dimensions of the data sets, my data.shape. So the number of columns, the number of rows 3994, number of columns 6. Just do have here. Now let's have our output. And the input data preparation. Let's start with the output or target variable. Y. So y equal my data. From my data we take area, flooded area. So to explore y dot head, just one area, one column. Y dot shape, column of 3994 rows. This is the area. This is how the inputs, variables or features, x equal my data. From my data we are going to drop time and our dependent variable, which is area. Point x dot head these are 4 columns we have, and x dot shape we have the dimensions of x. That's 4 columns, and in each column you have 2994 observation rows. Okay, we are done with our input and output data preparation. Now we are going to split our data set into training and testing. But before that, again, is run the variance inflation factor and the scale. Standard dies, standard dies, the features before we continue. Okay, so now splitting the data set into training and the testing. X text train, y train, text test, x train x test. Y train y test equal train test split. You have x, you have y, you have the test size. I take 30% time, and the random state equal to 30, and the shuffle equal to 2. It's wrong. Random state. Good. So taking the dimensions, we print explain dot shape x test dot shape y train dot shape y test dot shape. So here we have 2,795 observation in the training data set and the 1,199 observation in the testing data set. Okay. So the next step is to run the ridge regression. The first thing we need to do is to instantiate or initialize the model. Model instantiation, a model equal to reach alpha argument 1 to the power minus 5, have fit intercept equal to 2, we have a solver equal to Kolesky. Fit underscore intercept. And you run. But here you need to, let's say, run the hyperparameter tuning. Using your own data set to get your arguments or parameter values. These values, how I got them is through running my own hyperparameter tuning. the alpha enters the solver, the most important here. So you have to use your own data set, have your parameter tuning to get them. Okay, so now fitting the model on the training data set. So let's call it RG equal model dot fit on X train Y train. Okay, RG for regression. Now we are going to evaluate the training model as well as the testing model. So training model evaluation. So for this purpose we need to have a prediction on the training data set. So Y right here equal rg.predict X train. So now we need to print our R square. R2 underscore score observe Y and its corresponding predicted value. Then we print the mean absolute error on the training data set. Mean absolute error between the observed Y and the predicted Y. Then print the training MSE is the mean squared error between the observed and the predicted Y. Training. Sorry. Okay. Now we go to testing model evaluation. Likewise, here we need to predict the testing data set. So rg.predict X test, and then print the matrix. Testing R squared is R2 underscore score underscore here. Score this time predicted observe Y on testing data and its corresponding predicted value. We print testing in absolute error is mean absolute error can y test and the predicted. Observe y test and predicted y test. Print the testing. Let me see is mean squared error chain the observe and the predicted flooded area on the testing dataset. Good. Now let's go and run the k-fold cross validation. We need on both sides of the models, on both models for comparison purposes. So we run it on the training data set, then on testing data set. So let's call train CV equal to cross underscore var underscore score. Have x train first the model RG x train y train scoring equal to negative squared error and the number of folds equal to 10. The type train.cv to see the 10-fold corresponding errors and take the absolute mean value. So print the training or the absolute mean training CV score is absolute numpy np.mean of train CV. Okay, now we do the same on the testing data set. So test CV equal cross val score x test first model x test y test scoring equal to negative mean squared error and then CV equal to 10. Number of folds, error again, is scoring for negative mean square error. SV cross val score at the excess y test scoring negative mean score error x test not defined. Okay. So test CV then we have the absolute mean score. Print. Is absolute mp.mean with the mean of test CV. Okay. So we are good with modeling, with metrics on both training and the testing model. Now we go to running our SHAP. We already imported SHAP. Let's have the init JS again here, just to activate it. Okay, good. So we need to create an explainer. On the training dataset, or using the training dataset, this is to calculate SHAP values. Okay, explainer equal to SHAP dot linear explainer model RD and extrain. Good. Now we need the SHAP values for the training dataset. Outputting SHAP values on the training dataset. And then we'll do the same for testing data. So I have SHAP underscore values TR for training dataset equal to the explainer. We just created above here, explainer dot SHAP underscore values and extrain. So when we type SHAP underscore values and TR, this is what we get for the 2795 values. Rows, 2795 rows. Extrain. Dot shape. Yep, this. Let's see here. Dot means as continuous. Okay, good. So let's have some plots. RAM means the most important plots, training model. Okay. So let's have the summary plot. This is the combination of feature importance, range of feature effects, feature effect plots. So two plots at the same time. So to have it, we have SHAP dot summary underscore plot parenthesis. We have our SHAP values on the training data set. We have X-train, our training features, and the name of the columns. Feature names equal to X-train dot columns. So this is what you get. See here, feature importance, and we have the effects based on the values from low to high. We have the SHAP values impact on model on the right side of the plot, meaning our left side. This is the negative values. On the left side of the plot, or our right side, this is positive values. And the impact here, you see the colors high, low. So low negative values of soil moisture have low impact, with negative or affect negatively the flood, while high impact, high values here of soil moisture, they have positive impact. High values have positive impact on flood. And low have negative impact on flood. So the most important feature is soil moisture, and followed by air temperature. If you take precipitation, you see here red. So have high negative impact here. Negative values of SHAP correspond to high. Okay, there is a variance of this plot. It's very smooth. We just pass an argument called boolean. So let's SHAP dot summary underscore plot parenthesis SHAP values tr X-train feature underscore names equal to X-train the columns, and plot type equal to violin. Yep, so it's a smooth version of the first one, and the only difference is we pass violin here plot type equal by then. Okay, so now let's have another type of plot, which is the feature importance plot. We already talk about it briefly with the above plots. So features with large absolute SHAP values are important. Here again, it's almost the same code, but with the plot type we type bar. The only difference here. So SHAP dot summary plot. SHAP values here. Explain feature names equal to explain dot columns and the plot type equal to bar quote, bar in quote. So here is mean SHAP absolute value. In parentheses, average impact on model output magnitude. Average impact. The average impact, this is impact on model output, SHAP values. Okay, so for these three products, the codes are almost identical except the plot type. We put here. So there is another plot which is embedding plot. The embedding plot it projects as a 2D plots. Products with SHAP values, 2D plot, 2-dimensional using the PCA, principal component analysis, principal component analysis, for visualization purposes. Okay, so here we have SHAP dot embedding underscore plot parenthesis. Let's take let's by features. So take soil moisture. See here, this is the most important. So soil moisture. We have the type explainer dot SHAP values parenthesis explain feature names, feature underscore names equal to xtrain.columns. So this is what we get for soil moisture. If we change for 80, the second most important feature, we run, we see here SHAP values for 80. So the impact of 80 is in 2D. So you have from 0 to 1 and then from 0 to -2, how it spreads. Okay, good. So let's have the global bar plot. Explainer. SHAP values tier equal to explainer on xtrain. We are on the xtrain model, so xtrain. Then tab SHAP dot plots dot bar dot SHAP dot plots dot bar SHAP values tier. SHAP values tier. This is the global bar plot. And if you want the local bar plot, you're going to take SHAP dot plots bar SHAP underscore values tier and x0 because negative, positive, both. The global gives us only the main SHAP absolute values, absolute SHAP values, we mean. While the local gives us the SHAP values from negative to positive. Good. If you want the auto cohort feature plot, plot have SHAP dot plots bar dot plots dot bar SHAP dot plots dot bar SHAP underscore values tr, because we are still on training data set, dot cohorts in plural 2 by 2, so 2 cohorts 2 dot absolute dot mean 0. So So the values are the impact corresponding to when the values are less than or more than less than or more than equal to these values you see here. So again, here is the mean of the absolute SHAP value. Okay, if you want the feature clustering, cluster feature clustering plot, clustering for SHAP.utils .h cross and x train y train. Clustering for SHAP.utils cross x train y train. And then we run first x train. Okay, this is our clustering. Then now we are going to plot it. So SHAP plots bar SHAP values tr clustering equal clustering equal to clustering. So this is the second clustering. The clustering here equal to the clustering we put above here. So this is what we have. Which are the features? What are the features that are redundant? So these two, air temperature and the evapotranspiration. Here clustering is cutoff 0.5. So they are redundant. It means here. So if you want the waterfall plot, have SHAP plots waterfall. SHAP values here. Take the index. If you want the false plot, have SHAP plots false. Then SHAP underscore values here. This is the first plot. So we are done on the training data set. Let's output SHAP values on the testing and do some plots as well. So let's put SHAP values TS none, TS equal explainer, the same explainer we have created using the testing dataset. So SHAP values X test, no, this time above it was explain those SHAP values X train, now X test. So let's type SHAP values TS. So this is what we get. We will, so 1195, I think. Let's say X test. X test dot shape. Yep, 99. 1199. Yeah. So some plots here is also. Let's add more cells. Summary plot. So SHAP dot summary underscore plot. We have our SHAP values on TS. We have X test. We have feature names equal to X test dot columns. If you need the violins type SHAP dot summary underscore plot SHAP underscore values X test feature name equal to X test dot columns, and the plot type equal to violin. SHAP values TS. This is what we get. The feature importance plot. So the only thing that changes is the plot type is going to be bar. So SHAP dot summary underscore plot SHAP values TS X test feature underscore names equal to X test dot columns, and then the plot type equal to bar. Good. If you need the embedding, do the same. This time we replace everything by SHAP TS. So SHAP dot embedding plot parenthesis. Let's take again here the most important feature is still soil moisture followed by air temperature. So we have our soil moisture here. We have the explainer dot SHAP underscore values, this time on X test. And the feature names, feature underscore names equal to X test dot columns. So this is for soil moisture. We see the SHAP values, the vertical bar here. We go to negative, that's 2, positive values are 0 to 2, negatives up to -3. If you want to explore the others, just change the feature name here. This is this time for 80. You see the 2D plot. Okay. Now if you want the bar plot, global bar plot, SHAP values TS. Values TS. Equal to explainer. Explainer X test. Explainer X test. SHAP plots bar. We have the SHAP values TS. We need the local dot SHAP dot plots dot bar SHAP underscore values TS /0. The autocohort plot SHAP dot plots dot bar SHAP underscore values TS dot cohorts parenthesis 2 dot abs dot mean, absolute mean 0. Need to close again. Okay, need to remove this parenthesis. What's this? Good. Okay. Now we need, if we need feature cluster, because we did above, so we have to do on both sides in order to compare them on training and testing. So again, we create an object clustering here, which is equal to SHAP.which dot h class, present our class here, xtest parenthesis xtest. X and Y test as well. Then we plot the parenthesis is closed here. Okay, the clustering is already created. Then now we plot our SHAP plots. SHAP.plots bar SHAP underscore values just clustering equal to clustering. Here again, AT air temperature and ET air cluster, so they are redundant. And then on the waterfall, plot SHAP dot plots dot waterfall. Parenthesis SHAP values yes. Then you had force plot above, so you also need force plot here. SHAP dot plots dot force SHAP plot SHAP values yes. Then let's see. So this is what you have. So these are some plots that may be important for the interpretation of your results using SHAP. I select it here. So thank you very much for watching the video. We are at the end of it. So I hope it will help some people who are analyzing their models using SHAP to get some inspiration in order to make progress in the research. So Thank you very much for watching again, and see you next time for another video.